Hi, we are Team 1 and we will present our final project, Reprogramming MultiModality. We will start with the introduction. The world we experience is inherently multimodal. When we watch a movie, we simultaneously process vision, audio, and text. Even in a simple conversation, we are engaging multiple modalities such as facial expressions, body language, tone, and speech. This natural human ability to integrate multiple modalities is what people aim to achieve in deep learning systems. One powerful approach is training models to learn a multimodal joint embedding space. This is a shared representation where different types of data like vision, text, and audio are mapped together, allowing meaningful interactions between these different modalities. ImageBind is a recent study from Meta AI that demonstrates this concept in practice. This paper introduces a novel approach for learning a unified joint embedding space that integrates multiple modalities, including images, audio, text, depth, thermal, and even IMU data. ImageBind leverages the binding property of images. Like a single fire image naturally connects to its crackling sound and textual description. By training each modality to align with images, ImageBind creates emergent alignments between unpaired modalities, like between the text and audio of fire. This enables a more flexible unified embedding space. However, to align each modality with images, ImageBind requires separate encoders for each modality, leading to significantly increased computational cost during both the training and inference. Therefore, we propose using reprogramming technique instead of specialized encoders. This technique repurposes pre-trained models by mapping new types of data to the domain the model was originally trained on. By leveraging the existing capabilities of large pre-trained models, reprogramming significantly reduces the computational cost and data requirements. So with ImageBind as our baseline, but instead of using specialized encoders, we aim to map all modalities into the image domain with reprogramming layer by leveraging the binding property of images and the knowledge of the pre-trained image encoder model it uses. So this is our model's overall architecture. We use OpenClip as our image encoder following the baseline approach. For modalities other than images, video, and text, we first process them through dedicated tokenizers and reprogramming layers before mapping them to the image embedding space. Our reprogramming layer uses an attention mechanism matching OpenClip's VIT-based structure. The query is a learnable parameter matching the image encoder's input dimensions, while the key and value comes from the target modality's tokens, allowing the model to learn relationships between the image and the target modality embeddings. Through attention-based reprogramming and contrastive learning, we map the modalities like depth and audio into the image embedding space, aligning them with their corresponding image inputs. For our experiments, we trained the reprogramming layer using two modalities, audio and depth. And however, due to the limitations in computational resource, we utilized a smaller dataset compared to the baseline for training. We evaluate performance through zero-shot classification tasks, which are typically employed to assess the model's capacity to generalize cross-modality relationships. However, with our reprogramming method, we could not reach the baseline performance. We conducted ablation studies to better understand our model's behavior. First, comparing linear and attention-based reprogramming layers, we found that the more expressive attention mechanism achieved better performance. Additionally, we tested how the amount of training data affects performance. The performance remained relatively stable, suggesting our reprogramming method can be effective even with limited data. In conclusion, while we successfully demonstrated that reprogramming can work with limited data, our approach didn't match ImageBind's baseline performance. However, our experiments showed that more expressive reprogramming layers, like attention mechanisms, achieve better results than simpler linear layers. So for future work, We plan to explore more expressive reprogramming methods, which might help bridge the performance gap with the baseline.